Hi, welcome to my presentation for Physics 2212, Lab 3 on the magnetic field of a bar magnet. First, I will begin by introducing the purpose of the experiment and explaining some key fundamental physics principles, discuss data collected and values calculated from the experimental models, explain my accompanying computational model, and conclude by answering some additional questions. The purpose of this lab was to measure the magnetic field of a bar magnet and to determine the magnetic dipole moment. A few assumptions were made for this experiment, such as the fact that the bar magnet was treated like a magnetic dipole. Other assumptions include the fact that the magnetic dipole moment is in the same direction as the magnetic field, and the only magnetic fields present were that produced by the Earth and the bar magnet. Moreover, I assumed that the net magnetic field here in Metz, France, where this experiment was conducted, was approximately 48 microteslas, per the value given in the experiment's instructions. Lastly, I assumed that the experiment was correctly oriented to compensate for magnetic north. One major conclusion from this experiment included finding the magnetic dipole moment, mu, was equal to 2.06 am squared, which allowed me to calculate the magnetic field of the bar magnet. Some fundamental physics principles that relate to this experiment include magnetic fields, magnets and magnetic dipoles, and magnetic dipole moments. The magnetic field created by a dipole with a magnetic moment represented by mu at an observation location r relative to the dipole equals the second equation listed on the slide, which can be further simplified to the first equation shown, which is mu naught divided by 4 pi times 2 mu divided by x, or r cubed, assuming mu and the magnetic field are in the same direction. The magnitude of the magnetic field due to a bar magnet decreases as the observation location is moved farther from the bar magnet. This distance dependence can be expressed by the equation magnetic field is equal to k times r raised to the n, where k and n are found from experimental data. To set up the experimental models, the Earth's magnetic field was taken into account by rotating the phone until an x component was 0, making it aligned with the Earth's magnetic north-south axis. For this experiment, the Tesla meter app was used and the axis was defined. The location of the magnetometer chip in the phone was found and is located where the two upper edges of the tapes intersect. Next, I found a distance from the magnet to the sensor that produces a magnetic field with an x component of magnitude of 20 microteslas. This process is repeated 3 times and replicated for when the magnetic field equals 70, 120, 170, and 220 microteslas. The off-axis field was found by using the same experimental setup to find a distance, d perpendicular, for which the net magnetic field had a magnitude of 100 microteslas. The y component of the magnetic field was recorded, and the phone was moved to a distance d perpendicular, and the x, y, and z magnetic field components were recorded. The second part of the experiment was repeated 3 times. The data collected for this experiment is listed in this Excel sheet. Some important pieces of information collected include the distance of the phone from the bar magnet when the magnetic field in the x direction was about 20, 70, 120, 170, and 220 microteslas. A graph of ln of bx versus the ln of r is shown as well. The data for the second part of the experiment when finding the magnitude field of a point off the axis is shown at the bottom. Some important observations for this experiment include that when the magnetometer was far away from the magnet, it measured a near zero magnetic field in the x direction, but as the magnetometer moved closer to the magnet, the measured x component of the magnetic field increased. Some important calculations from this experiment are also listed. When plotting ln of bx versus ln of r, n was the slope of the line and k was e raised to the y-intercept. The magnetic dipole using each average distance was calculated using the equations listed, and then were averaged to find the magnetic dipole of the bar magnet. Mu is equal to 2.06 am squared. The magnetic field observed is also listed on the slide. The z component was neglected as it was assumed to be pointing out of the phone. The magnetic field predicted in the code, which will be explained next, is also listed. I created a computational model in GlowScript to expand upon the findings of my physical experiment, allowing me to predict the magnetic field as well. A link to my code is presented in the description of this video. In this section of the code, some important terms were defined. Additionally, the function for the magnetic field of the dipole and how the different observation locations, 2 on the axis and 4 perpendicular, were defined. These lines of code show how the arrows were created to represent the magnetic field on axis and perpendicular. Lastly, lines 82 through 100 show how the arrow for a magnetic field of 45 degrees off axis was created using the perpendicular distance found in the experiment. In conclusion, the magnetic dipole moment equals 2.06 am squared, and the values for the observed and predicted magnetic fields are listed. The observed values are larger than the predicted values, which could be due to sources of error in the lab, such as accidentally bumping the phone when adjusting the ruler, as well as nearby electrical equipment and steel iron objects or magnets nearby. Now, to discuss a few reflection questions, what would have happened if I had not oriented to compensate for magnetic north? The purpose of orienting the magnetometer with Earth's magnetic field was to eliminate it from the values found. If this hadn't been done, the graph would have had the same shape for the first part of the experiment, but the values for bx would be different and larger because it would have included the Earth's magnetic field. causing the value of mu to be different and creating a difference between the experimental and theoretical values from the first and second parts of the lab. And if two magnets were stuck together and the experiment run again, I would expect the x values to be significantly larger, but not necessarily 2 times stronger, and follow the same trend of the logarithmic graph. Thank you for watching.